Hey, hi everyone. So welcome to this week 9's lecture on the course on linear systems theory. So much of the first 8 weeks were focused on, of course, gathering tools from math, and the remaining part of it was devoted to lots of analysis of systems before even we start a design procedure or go about designing a system for a certain requirements, could be on transients, could be on steady state, and so on. And that kind of gives you also importance of the analysis part, which includes starting from stability till verifying conditions for stability, controllability, observability, and so on. So now we will slowly try to build up a case for why these tools were useful, or why this rigorous analysis was useful even before we start solving design problems, right. And then the next 4 weeks will exclusively deal on several design aspects of linear systems, starting from a controller design to an observer design, optimal control, or very basics of optimal control. And towards the end we will look at some of the computational aspects of the analysis tools that we had learned earlier in the course, right. So just before we go into design process, we'll just do the last part of the analysis, which kind of turns out to be quite useful and also elegant in its representation. Okay, so we start with what is called the Kalman decomposition. Right? So the question that we will ask today is, in week 7 we had talked about a controllable decomposition and defined for ourselves the notion of stabilizability, and the system is good to stabilize if and only if the uncontrollable part is stable, and so on. We had a weaker version of observability called the condition on detectability, and we also had a process of how we go about doing the observable decomposition of the system into its observable and unobservable part. And we kind of viewed these two as two independent features of systems, which in practice may not be the case all the time. We may have a system which is both uncontrollable and unobservable at the same time, right. So we will today look at methods or how to arrive for this decomposed models when I have both the system losing controllability and the system also losing observability. What is the appropriate transformation that will take me from the original system to the system which is decomposed explicitly in terms of its uncontrollable, unobservable modes, and so on. So there could be four possibilities that could exist. So if I just look at the standard controllability notion, I could decompose my system into the controllable part and the uncontrollable part. I'll call this NC bar in such a way that NC plus NC bar was equal to N. So I am just looking at the dimension of the controllable and the uncontrollable part. Similarly with the observable and the unobservable part. Okay, and again in such a way that the observable, the total dimension of the observable space plus the unobservable subspace is the dimension of the state space, right. So that is what we did, separate analysis both for controllability and observability. Okay, so now a system can have both the properties together, right. So we can now decompose or divide the system based on both of its controllability and observability properties by considering controllability and observability together. Okay, how that looks like. So it should be kind of pretty intuitive to arrive at this picture, right. So we could have a system which has both modes which are controllable and observable, like a part of the system could be both controllable and observable. A part of the system could be controllable but not observable. Similarly, a part of the system could be observable but not controllable, and there could be a part of the system which is neither controllable nor observable. and we say let us decompose this system into its 4 of this kind of subspaces, where the part which is both controllable and observable, I call it of dimension NCO, here which is neither which is controllable but not observable, I call it NCO bar, and the part which is observable but not controllable, I call it NC bar O, and this is a part which is neither controllable nor observable. Okay. So this would be its respective dimensions. Now these 4 dimensions together will satisfy the this relation, that all of the subspace will constitute Rn, right? A nice pictorial view of this decomposition. Okay, so before we come to the overall decomposition, let us individually revisit the controllable and the observable decomposition techniques. So first what we know is that a system which is not fully controllable can be transformed into its controllable mode, I call it XC, and the uncontrollable modes, I call them XC bar, right, in such a way that the XC dot, the BC influences only the first k components, and then the remaining n minus k are uncontrollable, right. And then this will come via some kind of a transformation which looks something like this, where Vc forms a basis for the A invariant controllable subspace C naught of AB, right. So this Vc was constructed through the independent the k independent columns of the controllability matrix C. Okay. Similarly, in the unobservable case, we know that a system which is not fully observable can be transformed such that it decomposes the observable and unobservable components in such a way, right. So these are my first, say, k observable modes, these are my unobservable modes, and C, okay, this need not be 0, but there can be something here like BC bar, and Y will be decomposed into its observable and the unobservable form, observable and the unobservable components. Again, the transformation will be V naught and V naught bar, where the columns of V naught bar form a basis for the A invariant unobservable subspace of the form of the transformation AC, and this V naught comes from again the observability matrix. Okay. So now we will see how to combine these two and get a decomposition for a system which is which can be both uncontrollable in some modes and unobservable in some modes. Okay. So this canonical Kalman decomposition would give us a similarity transformation which decomposes the system into its 4 components or modes and gives both controllable and observable pairs. So we know what is the transformation that gives us a controllable decomposition, that is, if I say XC, okay, let me write this all over here again. So I have XC bar was T inverse X, which was such that this T was a result of Vc and Vc bar. So I could just split it into, so this comes from the controllable subspace with the pair AC BC being controllable. Okay, and similarly what we saw was with the observability thing, that I have XO bar is in such a way that, so this decomposition comes via again some T inverse X, sorry, T inverse times X, where T was V naught bar. Okay. So this columns form the subspace, or these columns form a basis for the unobservable subspace, and these columns form the basis for the controllable subspace, as we saw just in the previous slide. Okay. So now can I write this, or can I find a transformation which combines both of these things, right? So in such a way that I have these 4 subspaces, controllable, observable, controllable but not observable, observable but not controllable, and neither controllable nor observable. So can I find a basis for each of these 4 subspaces? So VCO denoting the basis for the controllable and observable subspace, and so on, right? Can I find a transformation which then transforms my system to something like this. Okay. So, I have the decomposed system into its parts which are both controllable, observable, neither controllable, not observable, or either of them. Okay. So, this is what we will derive today, or how to find a basis which will transform my system to a form which looks like this. Okay. So, again XCO are the controllable and observable states and so on. Okay. Now, I can just draw a block diagram of this which looks like this, right. So, I have all the modes here starting from controllable, not observable till neither controllable nor observable. Okay. So, the other way of looking at how to arrive at this VC and VO bar is also via the singular value decomposition. So, I take the controllable matrix, and so I kind of try to find orthonormal basis for the controllable and the uncontrollable subspace, and this is given by the left singular vectors of in the SVD of the controllability matrix. So, the singular value decomposition of this C would precisely have these terms here, like VC and VC bar, which we derived earlier, and similarly for the observability matrix, here I will have V and VO transpose. So, this was the basis for the A invariant controllable subspace. This was the basis for the A invariant unobservable subspace. Okay. Now, so this is another way of looking at how to derive VC and VO bar, right. Okay. It's the same process. You could just verify it quickly. Okay. Now, how do we start for this, right. So, let's also write this down as we go by. Okay. So, let me just draw a little picture here, right. So, which will say, okay, I have this as my controllable subspace of say some dimension NC, and this is an observable subspace of some dimension NO, and there is some intersection here which will say give me the subspace which is both controllable and observable. Okay. Now, the aim is to find these 4 bases here, this VCO, VCO bar, VC bar O and VC bar O bar. Okay. So, now let us say I have okay, let us start with say that I want to find VCO from, okay, I know these two things, I know VC, I also know VR from this slides here, right, or even the previous ones. Okay, and possibly also maybe VO bar. Okay, now for some vector, right, so some vector which comes from so this vector xc naught is from that is this is fully within the controllable and observable subspaces. Okay. Now, this xc naught, so let us say okay, there is this okay, I just put this as a point and call this xc naught. Okay. Now, this xc naught is both in the controllable subspace and is also in the observable subspace, and therefore, it can be expressed as so xc naught is both in the controllable subspace and the observable subspace. Okay, I am just abusing the notation a bit, but it is good for understanding. And because it is in both observable subspace, it can be expressed as a linear combination of let us say this I call this as xc and I call this as xo of the basis vectors of the controllable subspace XC and the observable subspace X naught, which means that this X C naught can be written as, so we will just try to derive these three expressions. So, this X C naught is say some A1 V C1 till A N C V C N C. Okay. This can be written as V C times A. Okay. So, this is again you see that this X C naught, so X C is of dimension N C, and therefore, I will have N C basis vectors. This X C naught can also be written in terms of this space with its corresponding basis as say some B1 V, the notation we used was okay, VO, right, VO1 plus B and O, VO and O. I can write this as VO times B. Right, this is the dimension of the observable subspace. Okay, and this is also in this subspace, right, with I can also write this as some basis of VC naught, which is the subspace which is both controllable and observable, plus sometimes some vector C. Okay, so this vectors A and B are such that X C naught is both within the controllable and observable subspace. Okay. Now, what happens, okay, how do we write now given these two vectors, how can I find now a basis for VCO, like for this intersection space here. Okay, so where we are now, right. So, so for every X C naught in the controllable and observable subspace, there will exist a unique A and B which form their own subspaces of dimension NCO. So, this dimension is the dimension of this subspace which is both controllable and observable, and these are all the same vectors X C naught which is VC times A, VO times B and VCO times C. These are all the same vectors. Now, can we find again the basis for now VCO? That is what we will do right now. Okay, so let me say that okay, so let us say I'll go to a new page. Say consider the subspace of A to be spanned by some vectors, say A1 till A N C O. Okay, and similarly for B to be spanned by B1 till BNCO. Now, the basis for VCO given this, right. So, what do I have now? I have VC times A1, VC times A and C naught, this is VC times VA. Similarly, VC naught can also be written as VO times B1, VO times B and CO. This is VO times VB. Okay. Now, what is this VA here? VA is an N cross NCO matrix. Okay. And similarly, okay, this NC cross NCO. Similarly, VB is an NO cross NCO matrix. Okay. Now, what do I have now so far? So, this so the idea was, okay, since 5, 6 and 7 represent the same vector, we can find a basis VA and VB for subspaces spanned by A and B vectors such that A is VA times C and B is some VB times C. Okay. Now, that is how this basis is derived. So, this means that now I can write these vectors, okay, let us go here, that x c naught as V c VA times C, okay, or this also comes from this thing here, right. So, V c naught is V c times VA. So, I just do this here. So, therefore, x c naught would be V c VA times C, which essentially means that now compare this expression and this expression, which would kind of imply that that something like this holds true, right, which is also what we derived over here. V c naught is V c times A and V c naught is also VO times VB, right. Okay. Now the next steps, right. So, what do we do? So, I have this relation and I have this relation. So, let us quickly do something here. So, if I know basis for V naught or and V naught bar, we know that these are orthogonal complements. Which means V naught bar transpose V naught is equal to 0. Okay. Now, what do I know? I know that V c naught is V c times V A. This is also equal to V naught times V B. Okay. Now, what do I do is just pre-multiply this by this one. Transpose. Okay. Now, this is 0. Therefore, V naught bar transpose V c times V A is also equal to 0. Okay. Now, which means that this V A is in the null space of V naught transpose V c, okay, from here. Okay. Now, what is this V A? This V A is the basis for the coefficients A. From here. Okay. And therefore, now if I go one step further, what is V c naught? V c naught was V c times V A. Now, this is equal to V c. Now, where does V A come from? V A is just from the null space of V 0 transpose times V c, right. So, this is the first one, the relation that we derive. Okay. And this, okay, the steps are written also here. So, this is what we derived. V c naught is V c times the null space of V O transpose V c. Now, I know each of this, right. I know V c, I know this one, and I also know this one from the decomposition, which comes from somewhere over here. Okay. Similar steps I can derive now V c O bar, V c bar O and V c bar O bar, very similar steps. Okay. And then I just use this nice property here, right. And therefore, now with this steps I now know what is this T that will take me from a given system to its this decomposed form explicitly into its modes, which are both controllable and observable, controllable but not observable, observable but not controllable, and neither controllable nor observable. Okay. So, now what we have derived now so far is the following, like for every LTI system there is a similarity transformation which we just derived, that takes it to the following form in such a way that this pair is controllable and this pair is observable. You see from the expression you see like this is the controllable. So, you have controls entering here and no controls going here. So, these pairs these two pairs are controllable. Then, so this is a controllable pair, this is an observable pair. The triple A B C with A C naught, B C naught, C C naught is both controllable and observable, and the transfer function of the original system is the same as the transfer function of this one, right, of both the controllable and observable system. So, when we did the controllable decomposition, we proved that the controllable or the transfer function is the transfer function of only the controllable part. Similarly, if I do it for the observable decomposition, I get the relation that the transfer function of the system is only a transfer function of its observable part. Now, if I combine these two, I get this result that the transfer function of the system is the transfer function of both the controllable and the observable system. That is what we deal here, right, from this triple here. Okay. So, that is kind of nice. So, this leads us to now to define a concept of what is a minimal realization, because if I look at this system here, well, the system is of dimension n, okay, or you would expect that there will be n poles in the system, whereas if I derive the transfer function, it will just have poles which just have this number, right, from both the controllable and the controllable part and the observable part. Well, this is also a state space representation of the system, whereas I can go back from this transformation and still derive a state space representation of the system, and both are same, right. Even though here you define n states, here you will define only n CO states. Okay. Now, we will see how to actually get to a system which has only which only shows me the controllable and the observable form and just discards the remaining parts. Okay. So, now what is a realization, and I guess we all know this this derivation. So, given A, B, C, D, this is called a realization of a transfer function if I can do this. So, this is the relation between the state space and the transfer function model. Okay. Now, given the state space model, I can construct the transfer function. The converse problem is then called the realization problem. Can I go from, okay, this is a simple computation, or can I go from here till here? Okay. Now, the size n of the vector x is called the order of realization, right. So, here I started with a system which was like this, right. So, this in this realization, so this x bar was also of dimension n, whereas, well, if I look at the transfer function, it might just show me n CO number of poles, or that is the minimal order of the system. That is what we will derive now. Okay. So, now, well, this is not surprising to know there are many possible state space realization for a given transfer function, and they can be of different orders. I will towards the end do some examples on this and see how it goes. Okay. So, before this we need to define some small concepts called the Markov parameters. Okay. So, what are these Markov parameters? Okay. So, what I know from the relation between state space and transfer function and the tools from Laplace transforms is the following. Right? So, this I think I know this one. Now, what is e power at? E power at usually shows up as some infinite series. Okay. Now, Laplace of Ti by I factorial is minus S minus I plus 1. I think you should be able to derive this, and therefore, Si minus A inverse is nothing but the summation of summation over I equal to 0 till infinity s minus I plus 1 a to the power I. Okay. And therefore, the transfer function g of s, which was usually computed in the following form, that you have c then s I minus a inverse b plus d was d plus, okay, then I just substitute for s I minus 1 a inverse, I get summation of I equal to 0 till infinity s minus I, sorry, I plus 1 c a power I b. Okay. So, these two matrices D and C A I B for I greater than or equal to 0 are called the Markov parameters. Okay. And these Markov parameters are these parameters, the Markov parameters can be related to the impulse response of the system. Impulse response is also usually referred to as the natural response. So, therefore, G in T would be the inverse of G of S, and I do all the steps, and what I get is the following: C E power A T B plus D with the impulse function delta T. Okay. Now, just take some derivative. So, D G, the ith derivative T with D T I is C E, C with, okay, so A will show up here, A power I, E power A T times B, and okay, the D will no longer be here. Okay, from which we obtain the following relationship between the impulse response and the Markov parameters. So, the limit of T, okay, so of this D I G T by D T I is C A power I B, E power A T is the identity for all I greater than or equal to 1. Okay. So, these are the Markov parameters, and this is a little procedure of how they are derived. Okay. So, something which I will not prove, but just state as a result is the following. Say I have a system x dot is A x plus B u, y is C x plus d u, and another realization which looks like this, say x bar dot is A bar x bar B bar u bar, sorry, okay, the u will be the same, y is C bar x bar plus d bar u. Okay. These two realizations denoted by A B C D and A bar B bar C bar D bar are equivalent if and only if they have the same Markov parameters. Okay, I will not do the proof of this, but we will use this relation to prove results relating to the minimal realization. Okay, so what does the minimal realization now mean? Realization GS of, or a realization of GS is called minimal or irreducible if there is no realization of GS of smaller order, right? Or if I go from the transfer function to the state space, it must just have n states, or the minimum number of states. There should not be another n prime which is less than n. Okay. Now, when is this possible? Well, a realization is minimal if and only if it is both controllable and observable. Okay, so we will do spend some time just doing the proof of this. So, what does it say? Okay, first we will prove that every minimal realization must be both controllable and observable. Okay, so we again use the method of contradiction. Okay, so assume that realization is either not controllable or not observable. Okay, and therefore, by the Kalman decomposition, okay, we can always find realization of smaller order that realize the same transfer function. And therefore, contradicting minimality. Because what does the Kalman decomposition theorem also say is that C Si minus A inverse B plus D is the same as C, which corresponds only to the controllable and observable form. Okay, so that is kind of easy to check. Okay, so now the second step, the only if part. Assume, so we do the reverse thing. That's the reverse proof that assume that the system is both controllable and observable, but the realization is not minimal. Okay, so what does this say? Okay, so I assume that when the system is both controllable and observable, I can find a realization A, B, C, D that is not minimal, which means there exists some other A bar, B bar, C bar, D bar that is actually minimal, and then we will show that these two are actually the same. Okay, that there cannot be a realization which is minimal than this one. Right? There is actually the realization which we get from this assumption is actually the minimal one. Okay, so again I have a right. So this assume that this is the minimal realization with some dimension n, and say this is okay. Assume that okay this is not the minimal realization. Right? That's what we prove by contradiction. Right? That the system is controllable and observable, but this realization is not minimal, which means there exists another realization C bar, D bar, which has a realization n bar which is less than n. Okay. Now, I just look at the controllability and observability matrix of this guy, and say that O C, the observability matrix times the controllability matrix, C C A till C A n minus 1, B A B A n minus 1 B is, okay, I get a C B here, C A B here, C A n minus 1 B, and then here I get C A n minus 1 B all the way till C A. Okay. And essentially what are in these matrices are the Markov parameters. Okay. Now look at the other realization, right, which we claim is that there is some n bar which is less than n, which gives me the minimal realization. So this will be again C bar till C A n minus 1, I have B bar, A bar, B bar, A bar n minus 1 B bar, okay, which will be the following. Again I will have the Markov parameters now in terms of C bar, B bar, and so on till C bar, A bar 2n minus 2 B bar. Okay, now let me call this say star and star with a bar. Okay, now this star and the star with a bar realize the same transfer functions. Okay. Now, if they realize the same transfer functions, they must have the same Markov parameters. And that is what I say that. So, I assume that there is a realization A, B, C, D of one transfer function G S, okay, and the same transfer function also has some other realization A bar, B bar, C bar and D bar. Okay. So, these two realizations are come from the same transfer functions if and only if these are equivalent, right. That is what the result we stated earlier. Okay. Now, when they have same Markov parameters, what we have is O times C is O bar C bar. Okay. Now, let us say that say C bar has only n bar columns which is less than n, and therefore, which is rank is lower than n, and therefore, rank of O bar C bar is less than or equal to rank of C bar. This is less than or equal to rank of less than or equal to n bar, this is less than or equal to n, which contradicts the fact that if these two are similar, the rank here should be the rank here. Okay. And therefore, we conclude that okay, if whenever I assume that there is another minimal realization, well, that actually is not true, that will be a contradiction, and therefore, we can conclude from both ways that a realization is minimal if and only if it is both controllable and observable. We now prove that a minimal realization is both controllable and observable. We can therefore obtain it from the Kalman decomposition. So, I have the Kalman decomposition matrices A, C, O, both controllable, observable, both B also belonging to, this should be C. And so, the minimal realizations of all of our transfer functions are similar if, right. So, this A B, C, D and A tilde, B tilde are minimal realizations of G S, then there will always exist a similarity transformation like this. Okay. So, two minimal realizations of transfer functions are actually similar to each other in the same way as similarity relations between systems which were transformed maybe to the diagonal form or to the controllable form and so on. Okay. So, we will do a bit of an example and okay. So, just to note, because I will use a bit of the controller canonical form or the controllable canonical form here, that I just would like to refer you to this lecture notes or the videos of our previous course on control engineering. So, I will not spend time doing the controllable canonical form all over again, but we will take we will use these examples to do a bit of illustration of the minimal realization theory. Okay. So, I have so given this A, B, C, D, sorry for this I will have G of S, right, which comes from C S I minus A inverse B. So, I can just compute this as 4 over S square minus 2S minus 7, and this is an easy step to compute. Okay. Now, I write this system equivalently in the controllable canonical form, where let us say in the new form I have a pair A bar, B bar and C bar, which look like this. So, A bar will be, so A bar in the controllable canonical form would be 0 1 2 7, the new B would be 0 1 and the C would be 4 comma 0. Okay. So, again I do the transfer function from this, I convert this to the transfer function via again C S I minus A inverse B, and I get 4 over S square minus 2S minus 7, right, and therefore, I can like verify this this relation over here, right. Okay. So, that is one simple example here, right. Okay. Now, what we can just to also add one step is check if this minimal realization here is both controllable and observable, right, and you will actually find that this realization is both controllable and observable, and therefore, the system which we get start from here is actually the minimal realization. Okay. I will skip the steps of computing the controllability and the observability matrix. It should be a very simple exercise to check. Okay. Now, we will go from the transfer function, right. Can I find a minimal realization for the following transfer function? Okay. So, in the controllable canonical form, if I write down the state space realization, that will be something like this: 0 1 0 0 0 1 8 4 and a minus 2, with B being 0 0 1 and similarly C being 2 1 and 0. Okay. Now, from if I go again back to the from the state space of the transfer function, I can realize this, but check if A, B, C is both controllable and observable. Okay. And you can easily check that the system is not observable. You can just check from the rank of the observability matrix. Okay. And therefore, this is not a minimal realization. Okay. Now, check this transfer function, right. So, we can also write this in the following way: S plus 2 over S square minus 4 S plus 2 is 1 over S square minus 4. Okay. And then I can now write down the controller canonical form, the controllable canonical form and the observable canonical form, where I will have a new A, let me call this A bar, as say 0, 1, 4, 0, B bar will be 0, 1, and C will be 1, 0, C bar, and this you can check that it is both controllable and observable, and therefore this realization is actually a minimal realization and not this one. Okay, one thing you can immediately observe is whenever the transfer function, if you have can spot a pole zero cancellation, then okay, if you go from here till here, this may not necessarily be a minimal realization, because you kind of miss the pole zero cancellation here. So whenever okay, you just factor out these terms here and take into account any cancellations, then you will arrive at a minimal realization of the system. And therefore, when we also talked about the relation between the system losing controllability and or observability via pole zero cancellations, and this is a little we can also look at it from that point of view of to get some intuitive relation of things between pole zero cancellations and lots of controllability and observability. Similarly, you can also go from here till start with this realization, and of course it is easy to check that it is not controllable and observable. Go back here, do the pole zero cancellation, and then come back here. Okay, so that concludes today's lecture, where we talked about decomposing the system into explicit forms, starting from the space which is both controllable and observable till the space which is neither controllable and neither controllable and nor observable. And from that we derived what is the concept of a minimal realization of the system. Okay, so next time we will start with our results on controller design. Essentially this would mean, can I find a state feedback to achieve certain system performances. So we will slowly also relate to the performance specifications what we did for second order systems in an earlier control course on the peak overshoot, the damping, and so on. So we will begin a bit of motivation from there and then go about solving more complex design problems. And so that's coming up in the next lecture. Thanks for listening.